Alright, so welcome back to physics. Let's get this stuff going. So this girl right here, she's struggling clearly, and yeah, science and physics. So we're gonna have to talk about sig digs. The funniest thing ever. Sig digs. We got sig digs. Scientific notation and unit conversion. Oh, and formula rearrangement. Okay, let's go. So before we start talking about any of that, we have to talk about accuracy versus precision. So here's what they are. We treat them as the same thing, but they ain't the same thing. Accuracy is how true measurement is versus precision is how exact a measurement is. So let's break this down further. Let's say you're throwing darts and you're as bad as this person. This would have high precision but low accuracy. So precision is how exact a measurement is. This is precise because all three of your darts hit the same area. So you were a precise thrower, but you weren't accurate because if you were accurate, you would have hit the center. So this is high precision but low accuracy. This one, it's so based on what we told you, we can tell that this is low precision and low accuracy because first of all, accuracy is how true a measurement is. Some of the dots are fairly far, so it's not very true. It's not in the center, so it's inaccurate. And precision is how exact a measurement is. All three of your darts are in random spots. Basically, you're just chucking and hoping for the best. So there's low precision and low accuracy there. Now finally, this is me right here. I would have high precision and high accuracy because I'm the freaking best. And this shows that this measurement is true because it's accurate and I'm always hitting the middle. And I'm exact. All three of my throws are always hitting the middle. So precision, once again, is how exact a measurement is, and accuracy is how true a measurement is. So this stuff about probability densities and reference values, we don't really need to know. It's just comparing the different types of precisions and accuracies again. So let's look at something else. This is where we start understanding sig digs. So we have a decimeter ruler. So this is 1 decimeter right here, this is 2 decimeter. Now, if we were to break that up and make a line right there, we could estimate that that's 0.5 decimeters, right? And when we convert that to meters, we get 0.05 meters. So based off of this estimate, we know that this point right here is going to be 0.5 decimeters or 0.05 meters. Now let's insert another ruler at the same length. So this we inserted a centimeter rule. So now we see that the 10 centimeter mark is on the 1 decimeter, which means it's accurate. But now look here. We thought it was 0.5 decimeters, but when we inserted the actual thing, it's not on the 0.5, it's in the 0.45. So now we learned that it was actually 4.5 centimeters and 0.045 meters. Now 0.045 meters is much different than 0.05 meters. Now once we use a millimeter ruler, we see 45.5 or 0.044455 meters. So the more digits that we have in our measurement, the more accurate our measurement is. So the number of significant digits actually matters. So how many in your number, how many sig digs are there? So now let's learn how to read sig digs. So this is just showing it again. 0.05 meter, 0.050 meter, and 0.0250 meter. So significant digits reflect the precision of the measuring instrument that you are using. So the only time a number does not count as a significant digit is that if it's a leading zero. So let me break this down once again. In this number right here, 0.05, how many significant digits are there? There's only one, the 5. But in this one, 0.050, how many significant digits are there? There's 2, the 5 and the 0. And in this one, there's 3, 5, 0, and 0. So zeros in front of the number, which is this 0 and this 0, they don't count as sig digs. So leading zeros do not count, but trailing zeros do count, and any number, any whole number does count. So as we see here, 1 sig dig, because the leading zeros don't count, 1 sig dig. 2 sig digs, because the trailing zeros do count, 2 sig digs. 3 sig digs, 3 sig digs. Digs, nigga. Now let's go on to talk about scientific notation. So scientific notation we have to use when we get an answer that's a large answer and we need it to the correct number of sig digs. It's certain situations we'll actually have to round it using scientific notation, such as if we were asked to put it in 3 sig digs, but it's a 6-digit number, how can we do that? So we have to put it in scientific notation. So it has the form a number point zero zero or another number times 10 to the some number. So let's just understand how that works. It just means that it could be anything from 4.63, 4.64, any number down here with the decimal place times 10 to the power of something. So we round off the last remaining digits of our intermediate answer and we use them. So if this exponent is a positive number, that means that your final answer that you get, it'll be bigger than 1. And if it's a negative number, that means your final answer that you get will be less than 1. So 3, 5, 6, 9. Let's say we got that as our final answer, but we needed it in 3 significant digits. How would we do that? Well, it would be you use the 9 to round the 6. So 3.57 times 10 to the 3. Yes. Now this number is smaller than 1, so we know that it has to be a negative exponent, and we need it in 2 sig digs. So the 6 will round up the 5. So it would be 4.6 times 10 to the power of negative 4. Okay? So we can just use trial and error in our calculators to figure that out. So standard notation is the number in how we would normally write it, and scientific notation is how scientists write it. So that number becomes, we need it in 2 sig digs in scientific notation, so we have to round up. Oh, I have a marker, damn. So we use this 3 and round up the 2, or keep the 2 the same, so 1.2 times 10 to the 5. Then for this one, if we want to convert back, it'll be 300. Bang, bang. Ooh. Now we want this in 2 sig digs, so we use the 6 to round up that, so 4.7 times 10 to the 3. Oh, 10 to the 2, shit. Yeah, shit, that's my bad. And this one is to the negative 4, so 10 to the 6 and negative 4, it's really easy. This one will be to the negative 3, 5.7 to the negative 3, yes. So now unit conversion. How we convert units by using the factor label method. So let's analyze that. It's all about the ratios, like your Instagram likes and shit. So if we were to convert 30 kilometers per hour to meters per hour, here's how we would do it. We would write 30 kilometers per hour multiplied by 1 kilometer down here to cancel out that. And we want to cancel out the hour by putting another hour here. We don't need to do that yet, sorry. Then 1,000 meters are in a kilometer. The kilometers cancel out. So it'd be 30,000 meters per hour. And then sig digs, because we have to get 2 sig digs back. So if we were to convert this to kilometers per second, now we have to convert the hours into seconds and the kilometers into, oh no, we keep the kilometers the same. So how many we have to cancel out the kilometers. Oh no, we keep the kilometers. We have to cancel out the hours. So hours and hours cancels out. And how many seconds are in an hour? Well, there's 3,600 seconds in an hour. So the hours cancel out, and 30 times 3,600 gets you that number. Sig digs gets you that number. Now convert 30 kilometers per hour to meters per second. So now this one we have to use the 3-way factor label method. So we have 30 kilometers per hour. Now we have to cancel out the kilometers to get meters. So here we would put 1 kilometer, and up here we're going to put 1,000 meters. Yes, there's 1,000 meters in a kilometer. Now we have to cancel out the hours, so we're going to put the hours up here. Oh, wait, it'll go up here, the hours, and down here it'll put how many seconds are in an hour, which will be 36. Oh my god, 100. So 1 hour, 3,600 seconds, like I said, and the hours cancel out. So essentially what you're going to do is 30 times 1,000 multiplied by 3,600, and that gets you that. Sig digs gets you that. Finally, the last one we use is 27.8 meters per second. Convert that into kilometers per hour. So let's see how we would do that. So we take the meters per second, and first what we want to do is cancel out the meters. So meters is going to go down there. 1,000 meters in 1 kilometer up here. So the meters cancel each other out. Now we want to use cancel out the seconds. So we would put 1 second, 3,600 seconds up here is in 1 hour. Seconds cancel out. So 27.8 times 1,000 times 3,600 gets you 100.08 kilometers per hour. Sig digs gets you 100 kilometers per hour. Now, this is the harder one. This is for acceleration. 1.27 times 10 to the 5 kilometers per hour squared to meters per second squared. So that's a four-way cancellation. So 1 hour squared, you put that down here, 1.27 times 10 to the 5. Now we gotta cancel out the kilometers. The 1 kilometer, 1,000 meters, they cancel out. Now we have to cancel out the hours here, which is the 1 hour squared. And we also have to take 3,600 seconds, which is in an hour. And we have to do it again, 1 hour squared and 36 seconds. This takes out the hours squared. So now what we have is 3,600 times 3,600 times 1,000 times the original number gets you that. Sig digs gets you that. Now the last aspect I'm going to talk about, formula rearrangement. So that's getting the variable you're trying to solve for, the target variable, it could be speed, force, mass, acceleration, whatever, on one side of the equation. So let's see how that goes. General strategy is you want to isolate the variable that you're moving. So first move the terms, so the groups of variables in equations that are separated by the positive and negative signs, and then you undo attachments. So let's look at how that goes. You want to try and isolate, in this one you want to try and isolate let's say you wanted to isolate the acceleration right here, right? So what we would do, you have this number being subtracted by this large number. First, you would just subtract all this off, and it would go right here on this side. So it'd be negative VFT or D minus VFT. So velocity final and time. And now you have this. So what you would divide this all by is negative 1/2 and t squared. You want to leave acceleration, and you do the same thing here. So your new equation would be acceleration equals the displacement minus velocity final over time divided by negative 1/2 time squared. Bang bang.